All right. Today we're going to distinguish between electric interactions in two different types of materials. We're going to define and talk about conductors versus insulators. And simple definition, basic difference between the two is that a conductor has mobile charges that are free to move. Hence the name mobile, just to drive it home, that are free to move throughout the material. And insulators don't. That's basically it. Insulators don't have mobile charges. Okay. So what we've been dealing with so far, the case of the tape, for example, is an insulator. Insulators, we have charges. We have positively charged nuclei and electrons bound to those nuclei. But the key idea is that those electrons are bound to the individual nuclei and can't move, at least not very much. Okay, they can shift a little bit. The electron clouds in the atoms or molecules can shift a little bit, but they're not free to move throughout the material. Okay, so when you're looking at an insulator that's polarized, so here is some block of an insulator. What's an insulator? Examples of insulators. What kind of materials are insulators? Wood, plastic, rubber is an insulator. Okay, a lot of organic materials, right? A lot of things having like hydrocarbons in them are insulators. So let's say we have a block of plastic and we bring a positive charge nearby. It's a neutral piece of plastic, and my markers are dying a little bit here, so let me grab another. And it polarizes, and the way we said we indicate the polarization is that we can think about the individual molecules actually becoming induced dipoles. Okay, and if I were to draw, in fact, this is a point charge. If I were to draw the electric field due to that point charge, it's kind of pointing away like that, right? So to make it is to give the sense that this is polarization due to this electric field. I'm even drawing the dipoles kind of lined up in the direction of the electric field. And if you wanted to indicate, since the field, the polarization or the dipole moment is proportional to the field, if the field drops off with distance, we can kind of draw a less elongated dipole farther away to indicate it's not quite as polarized. But the key idea in the way to represent this in sort of this cartoonish way is that you're drawing the individual molecules and showing a polarization for each molecule or for each atom. Okay, so each individual atom becomes polarized, or it becomes an induced dipole, and so the whole material is polarized. But the atoms or the electrons still stick with the nuclei. The electrons are not free to move around the entire material. Okay, so that's a polarized insulator. And of course, with the tape, we saw a case of where we had excess or net charge on an insulator. And the key idea here is that if you're able to place a net charge or an excess charge on an insulator, excess charge tends to just stay put. Okay, so let me write it that way. What do I mean by that? Well, I could do this. Let's say I have this little piece of plastic, like Lucite or Lexan or something like that. And I'll do another contact interaction, another surface interaction, and charge up, put an excess charge on the piece of plastic by rubbing it with some silk. And I'll just rub one end. And it will turn out that the charge, if there's any charge at all, will just stay where I placed it, where the contact interaction occurred. It'll just stick there. It won't spread throughout the entire material. And I can again show that if I charge this end with the same material, give it the same charge. So if I bring the two charged ends together, I should see a repulsion, maybe. And I do. Oh, that's satisfying. So we see these two charged ends repelling. If I brought this end to that end, what should I see? Yeah, I should see an attraction, right? Now, it might be a little hard to see because there's kind of a lot of friction on this little pivot here. But if I bring a neutral end to the charged end, I got to get close. Oh, yeah, I can. It's starting to go. Oh, that's pretty nice. Yeah, almost. Okay, it almost works, right? It's just a lot of friction on that pivot. If I bring the neutral end to this neutral end, I should see nothing at all. Okay. So the key idea here is the charge stays put. It stays where I placed it. I rubbed this end. You didn't see the charge spread throughout the entire object and charge up the entire rod. If you had, I would have seen a repulsion between these ends, right? So insulators, the charge tends to stay put. And because of that, why does that happen? Well, because there are no mobile charges. You stick excess charge in one place. There's no mechanism by which it can move throughout the entire material. You can place excess charge on the surface, which is easiest to do with these sort of surface interactions, or in the interior. Now, it's kind of difficult in practice to place excess charge in the interior of an insulator. But one way I could do it, for example, is if I had one surface that I charged up, one surface of an insulator I charged up, and I just glue it to another insulator, okay, just stick them together with some glue, and now I've got some excess charge in the interior, and it will just kind of happily stay there because there are no mobile charges for it to move around, okay? So charging in the interior is okay, charge on the surface is okay, and it just kind of stays put where you place it.